In this lesson, we are going to learn about activity of a radioactive substance and also learn some important points about radioactivity which will help us in solving problems. Activity means decay rate. Okay. Activity we write as R. R is decay rate, that is minus dN dt. That is what is activity. And this we know is lambda n. Right? So what is R? R is lambda n. But n is n naught, e to the power minus lambda t. Right? Therefore, R becomes lambda n naught e to the power minus lambda t. This lambda n naught is the activity at time t equal to 0. That we call it initial activity, R naught. Therefore, R becomes R naught e to the power lambda t minus lambda t. And this R naught is lambda n naught, that is called initial activity, activity at t equal to 0. The SI unit of decay rate is becquerel, named after the person who discovered radioactivity. So, becquerel is the SI unit. This becquerel is nothing but 1 decay per second. 1 decay per second is called becquerel. The other units which are not SI but are there again for historical reasons, 1 curie. This is really big. This number 3.7 is big, multiplied by 10 to the power 10 decays per second, or we can call it becquerel. So 1 curie is 3.7 into 10 to the power 10 decays per second. 1 Rutherford, another unit of activity. This is equal to 10 to the power 6 decays per second, or becquerel. Same. Now, how to avoid confusion? The number here is big and the power also is big for curie. Curie, the number is big, the power is big. This is activity of a radioactive substance. Now, let us talk about some important points that will help us in solving problems on radioactivity. First important point. After n half-lives, n small n, half-lives, the number of nuclei left will be n naught, the initial number of nuclei, half to the power n. Because every half-life, the number becomes half. Therefore, the number of nuclei left will be n naught half to the power n. The fraction of nuclei left will be half to the power n, right? Very obvious. The percentage of nuclei left will be half to the power n into 100. Simple. And the activity will become R naught half to the power n. All these things, every half-life, they become half. Next important point about radioactivity. After n half-lives, the number is becoming half to the power n. And we know the radioactive decay law, n equal to n naught e to the power minus lambda t. What is the probability of survival of a nuclei at time t? So, P survival will be given by n by n naught. N number of nuclei are there. Now, initially they are n naught. This is e to the power minus lambda t. This is P survival. At time t equal to 0, our nucleus will definitely survive. because it not started decaying. At time t equal to infinity, all the nuclei will decay. So P survival will be 0. So this is how P survival varies with time. This is P survival. This is time. If it does not survive, it decays. So P decay will be 1 minus P survival. So P decay with time will be like this, exponentially increasing. At infinite time it will become 1, that is decaying sure shot. So this is how P survival and P decay vary with time. P survival decreases with time, P decay increases with time. Next important point. In equal time, equal fraction of nuclei is decayed. Suppose in 1 hour, 10% are decaying. In the next 1 hour, 10% of whatever are left, that will decay. So every 1 hour, 10% will decay. And if 10% are decaying, 90% will survive. In equal time, equal fraction of nuclei decay, or we can say equal fraction of nuclei survive.